Welcome back to The Explainer. Today, we're doing something really eye-opening. We're putting a hard, real number on the actual cost of magnetic core physics. If you've ever found yourself wondering why our power infrastructure wastes energy before it even does any real work, well, you're in exactly the right place. We're about to uncover those invisible forces that are quietly draining power 24 hours a day, 7 days a week.
So, let's kick things off with a super quick recap of our last session. Remember how we talked about the physical build of the core? We saw that cores are laminated. They're built from these incredibly thin, coated steel sheets instead of just a solid block. And why? Specifically to cut down on those pesky eddy current losses. Plus, we learned that flux density directly trades off against core size. Basically, if you want lower flux density to cut your losses, you're going to have to build a bigger, heavier, and definitely more expensive iron core.
Okay, moving into Section 1, the core loss formula. Let's track down that wasted energy.
Now, the total core loss formula is strictly defined as hysteresis loss plus eddy current loss, and we measure all of that in watts per kilogram of core steel. I know it looks like an elegant, super simple equation right now, but trust me, it represents a massive amount of engineering effort just to minimize those two distinct variables.
Let's actually break those components down for a second. Hysteresis? That comes from basically forcing the magnetic domains inside the steel to flip back and forth, realigning over and over as the alternating current field changes direction. Eddy currents, on the other hand, are these little circulating electrical currents trapped right inside the core steel itself. And like we talked about before, we minimize those eddy currents by making the laminations incredibly thin, usually right around 0.23 to 0.35 millimeters, and by adding a specialized insulating coating. But here is an absolutely crucial warning that comes with all this physics. The literal second you energize that transformer, these core losses, they're locked in. They are totally constant. It honestly doesn't matter if you have absolutely zero load connected to the secondary side. Even if the transformer is just idling there on the network, doing nothing, it is continuously drawing power just to maintain that magnetic field. So zero load definitely does not mean zero loss.
Which brings us to Section 2, the paperclip analogy. Let's visualize this hysteresis.
To really translate all this abstract physics into something you can kind of feel, think about this. Efficiency ratings are actually mostly a core design story, not a copper story. And that's because the core is doing something completely different than the useful work of the windings. The copper windings are out there actively transferring power to the load, right? But the core? It's really just the flux highway sitting right in the middle, quietly generating heat the whole time it operates.
Think of magnetizing that core exactly like bending a metal paperclip back and forth. We've all done it. If you bend a paperclip rapidly, you know it gets pretty warm right at the crease. Every single bend generates a little bit of heat, and it's doing absolutely zero useful work. Now, imagine bending that same paperclip 50 or 60 times a second. Forever. That is exactly what those magnetic domains are doing inside the steel. Crazy, right?
Let's put a real-world figure to this invisible friction. Say you have a 1000 kVA transformer, and it has a highly efficient design with just 2000 watts of no load loss. Now, 2000 watts might not sound like a huge deal for a massive piece of utility equipment, but because that thing runs 24/7, that tiny baseline burns roughly 17,500 kilowatt hours a year, just doing nothing but sitting there, energized. Okay, moving to Section 3, the lifetime cost. Let's look at 20 years of idle losses.
Let's try to bridge the gap here between the pure engineering and the actual economics. Time for a quick interactive check. I really want you to think about this. Over a typical 20-year service life, do you think this invisible, always-on core loss can eventually cost more than the initial purchase price of the transformer itself? What do you think?
The answer is yes. A resounding, absolute yes. Having a few thousand watts running continuously for 2 straight decades adds up to a massive and often completely overlooked financial line item. In a lot of grid applications, the cost of all that wasted energy just steadily accumulates until it literally dwarfs the initial capital cost of the hardware itself.
And honestly, this is exactly why you're always going to see no-load loss so rigorously documented on factory acceptance test reports. It's measured using these incredibly precise watt meters while the secondary winding is just left wide open. This test isn't just some boring regulatory checkbox, it proves the actual core efficiency, and it completely dictates that true 20-year running cost. It basically takes the abstract physics of magnetic domain alignment and turns it straight into cold, hard financial reality.
So you can now confidently look at a no-load loss test
and understand exactly why the core dictates the entire baseline cost of the grid. But, it does leave us with one massive question. If millions of transformers are burning thousands of watts right this very second, just sitting idle, how much of our global power generation is wasted before it even reaches a single home? Next time in the Explainer, we are going to wrap copper around this core and see how winding connections change absolutely everything. Until then, keep questioning the grid.